Okay, what about that tin lead system? This is a famous material used for many solderers. And so we can look at this area, and it's largely similar. We have here an alpha domain, and opposite on the other end, another beta domain. Way at the top, we have our liquid, and the melt points for the pure lead upwards of around here, and for the pure tin, a little lower over here. And if we have a true eutectic point, the melt point should be lower than both of those, and we should be able to go from a liquid to two different solids at that point. So we have our eutectic point here, just at about just below 200 degrees C. So fairly modest temperature considering we have metals involved here, and this is easy to do with a soldering iron to allow for us to reach temperatures in the green area and then cool upon removal of the soldering iron to form our two solids. Okay. So what about a question where we're asked at the 40 weight percent tin and 60 weight percent lead alloy condition at a certain temperature of 150 degrees to determine a few things. So let's determine which phases are present. So using the coordinates here, we know that we have to be at the 40 mark. And we've got to climb all the way to 150 for our point of interest. And so the phases that are present, well, we see that we're in the bottom area, so that's where there's both alpha and beta present. Okay. So let's just clean that up and we'll get the animation in there for us. Okay. Good. What about the phase? What are the compositions of these? So that is to say, now that we know that there is both alpha and beta present, what is the content of tin in the alpha? So we'll use the tie line here to help us with that. And so for the alpha, when we walk all the way over to the alpha domain and we track down, we would get our answer for that. And likewise for the beta, the amount of tin in the beta, we would walk all the way till we meet up with that beta phase and climb all the way down. So doing that, we see that the alpha is about 11% tin, and we get to very, very high tin content for the beta phase. That is to say, it is 99% tin. And then for the weight fractions of each, so if we're to do the weight fraction of alpha, we're going to do S divided by RS. And so we're going to have 99 minus 40. So 59 divided through by 99 minus 11, 88. And for the L fraction, here we're going to have the complement, so R divided by R plus S. Same denominator there, 88. And now we're going to be 40 minus 11, so 29 this time. Okay, so let's clean that up and see how those look. Okay, so weight fraction of the alpha here is 67%, and the beta phase is 33%. The 67, the majority material by weight, as we saw, was only 11% tin, and the minority component here, 33% by weight beta, is very, very rich, almost pure tin. Okay, looking at that same diagram now, just sort of zooming into very very low tin content area. So notice we're between 0 and 30 on our x-axis. we can consider what might happen as we work with a molten sample at about concentration of tin of just less than 2%. So looking at the morphology, let's consider what happens. So if we started at very high temperature, on the order of 350 degrees C, we would have pure liquid. And we know that the concentration of that tin would match the overall, so that would be about 2.8%, if that were the case. Okay. And then as we cool, you can see that we are forced to just slightly cross into the two-phase field that is liquid plus alpha. So at this point, we will generate some alpha particles on our way down to low temperature of approximately room temperature. And once we travel across the next phase boundary into the alpha area, we can expect all the green to disappear and all these little blue alpha particles to be the areas where further alpha phase is growing from. Ultimately, these will coalesce and they will take on composition that matches the x coordinate here for the purple line at a value that's at most 2% in tin. Okay. I'll just say it. And then as you were to cool even lower and lower all the way, you would never really change from this condition. Okay. So we've done this part to help us with now understanding what will happen if we look at making a sample that's a slightly higher concentration of tin, and what happens when we move from the alpha to the beta. What's going to happen as we try to create beta solid from a material that was in this sort of purple area and only had alpha solid. What might happen? Okay, so here, let's look at that condition. So we might be between about 2 and 18% tin for the scenario that we're about to describe here. We would again start with molten material with that concentration between 2 and 18%. And then as we start to cool it, we would expect alpha particles to form, very similar to what we had before. The content of these might be quite a bit different, given that we're well within the white space, and the tie line will tell us weight content of each, as well as the nickel, or as well as the tin content. And then as we kind of decrease the temperature past this point, we'd expect all the green to disappear and add alpha phase everywhere. So we'd expect to see that polycrystalline blue area again. And again, the concentration there would be uniform this time, matching the concentration that we have for the x-coordinate of our purple line, and similar to what we had up here. And then once we cross this temperature here of about temperature equal TE, we're going to see something kind of interesting, where we know that we now have to generate an additional phase using this as our starting structure. So somehow beta particles have to be generated using alpha. Okay, and so what we see there are small little beta particles form within the grains of the alpha that we had before. So these beta phase particles are now located within the alpha phase. And so you can imagine these might be useful for the precipitation hardening approach that we know to prevent shear planes from moving in the material when it's under stress.